Right now, light is passing through you, not metaphorically, not as a figure of speech. At this precise moment, photons from the sun are streaming through the walls of the room where you sit, passing through your skin, your muscle, your bone, and continuing outward, the other side, as though you were not there at all. Neutrinos, subatomic particles produced in the nuclear furnace of our star, are passing through your body at a rate of roughly 65 billion per square centimeter per second. They do not slow down, they do not notice you. To a neutrino, your body and the entire planet beneath it are indistinguishable from empty space. You are, at the subatomic level, almost entirely nothing. A lattice of forces and probabilities arranged into the temporary illusion of something solid. And yet here you are, aware of it. That tension between the physical insignificance of your body and the staggering improbability of your consciousness is the thread that will run through everything we are about to explore. Because we are going on a journey today. Not a metaphorical journey, a precise, quantitative, step-by-step traversal of the actual structure of the cosmos, from the dimensions of a human body to the outermost boundary of the observable universe. And at every step, something that seemed incomprehensibly large will be revealed as a rounding error inside the next scale. Every horizon you reach will open onto a larger horizon behind it. Every frame of reference you adopt will be swallowed by a bigger one. The universe does not merely contain large distances. It is recursively, systematically, structurally humbling in a way that no single number can capture. It is not that the cosmos is big. It is that bigness itself loses meaning before you are even halfway through the story. But here is what most people get wrong when they try to grasp the scale of the universe. They approach it as a matter of imagination. They close their eyes, try to picture something very large, and settle for a vague feeling of awe before moving on. That approach fails every time. The distances involved are not beyond imagination because they are too emotional or too abstract. They are beyond imagination because your brain was built by evolution for a specific and very narrow purpose, navigating the surface of a single planet at walking speed. The neural hardware you are using to process these words was shaped by millions of years of selection pressure that had absolutely nothing to do with galaxy clusters or cosmic filaments. Your spatial intuition is exquisitely calibrated for distances between roughly 1 centimeter and roughly 100 kilometers. Outside that range, your brain substitutes the word big for genuine comprehension and moves on. What we are going to do instead is something different. We are going to build the scale of the universe one concrete step at a time, always anchoring each new distance to something your body already knows. We are going to use numbers, but we are also going to use models, physical, tangible comparisons that give those numbers a weight your nervous system can actually register. And we are going to pause at each step to sit with what the numbers mean, not just what they say, what they mean. If that sounds like the kind of journey you want to take, one that will leave you looking at the night sky with completely different eyes, then do me a small favor before we begin. Hit that like button and subscribe to this channel. It costs you nothing, and it genuinely helps this channel reach more people who are searching for exactly this kind of exploration. Every subscription matters more than you might think. Now, get comfortable. Take a breath. Let's begin. You are in all likelihood somewhere between 5 and 6 feet tall. Call it 6 feet for simplicity, 1.83 meters. That number is your baseline, every distance your brain has ever processed, every hallway you have walked, every road you have driven, every horizon you have ever seen has been filtered through a nervous system calibrated to that height. 6 feet is the unit your intuition runs on. It is the ruler against which everything else gets measured, consciously or not. The tallest structure ever built by human hands is the Burj Khalifa in Dubai, completed in 2010. It stands 2,717 feet tall, roughly 828 meters. To build that intuition, you would need to stack approximately 450 people, each 6 feet tall, standing on each other's shoulders to reach its antenna. Standing at the base of the Burj Khalifa and tilting your head back, the top vanishes into haze. Your neck aches. Your sense of proportion wobbles at its foundations. It is the tallest thing most people will ever stand beside. It is also nothing. Mount Everest rises to 2,932 feet above sea level. That is nearly 11 Burj Khalifa's balanced end to end. Climbers who have stood on its summit describe an experience of standing at the boundary of the atmosphere itself. The sky above, deepening to an indigo so dark, it begins to look like space, the horizon curving almost imperceptibly in every direction. The air, at that altitude, contains roughly 1/3 the oxygen of sea level. Unprotected, you would lose consciousness within minutes. The summit is genuinely hostile to the existence of a human body, and yet Everest is a surface scratch on a planet. Earth has a diameter of approximately 7,918 miles. Let us round to 8000 for ease. If you could somehow drill straight through the planet from one side to the other and drive through the tunnel at highway speed, the journey would take just under 5.5 days of continuous driving. The circumference at the equator stretches 24901 miles. A commercial airliner, traveling at 550 miles per hour, would need slightly more than 45 hours to circle the entire globe without stopping. 2 days in a plane and you have wrapped around an entire world. Your brain can almost hold that. It strains, but it holds. Now consider this. If you shrank the Earth to the size of a billiard ball, one of the smooth polished spheres used in pool, it would actually be smoother than that ball. The highest mountains and deepest ocean trenches, scaled down to billiard ball proportions, would be nearly imperceptible to your fingertips. The surface of the Earth, which from the inside feels jagged and violent and enormous, is at planetary scale essentially a mirror finish. The oceans are a film. The atmosphere is a breath. The entire biosphere, every living thing that has ever existed, every ecosystem, every food chain, every organism, from bacteria to blue whale, occupies a layer thinner, proportionally, than a coat of paint on that billiard ball. Everything you have ever known lives in that coat of paint. The International Space Station orbits Earth at an altitude of approximately 250 miles. Astronauts aboard complete one orbit every 90 minutes, traveling at 17500 miles per hour. From their windows, Earth fills most of the view. Continents drift past below. Hurricanes spiral like white pinwheels. The planet looks enormous, alive, and impossibly beautiful. The astronauts float in what we call space, and they are indeed above the atmosphere, above the weather, surrounded by vacuum. But they are barely off the surface. If Earth were a basketball regulation size, roughly 9.4 inches in diameter, the International Space Station would orbit at a distance of approximately 1/16 of an inch above its surface, less than the thickness of a fingernail. You would need a magnifying glass to confirm the gap existed at all. The entirety of human presence in space, every crewed mission, every spacewalk, every moment any human being has floated free of Earth's surface, has occurred within that fingernail's width. That is the full extent of our physical reach into the cosmos. And yet those 250 miles feel remote when you are standing on the ground looking up. This is the first and most important lesson of the journey we are taking. Your sense of scale is already broken before you have left the planet. The distances that feel enormous from ground level, the 250 miles to the space station, the height of Everest, the diameter of the Earth itself, are so negligibly small on the cosmic scale that they will shortly round to zero. Not approximately zero, not close to zero, zero. They will become invisible, unmeasurable, beneath the resolution of any map we could draw. The Moon changes things slightly. Earth's nearest celestial neighbor orbits at an average distance of 238,900 miles. To picture that, using our basketball model, the Moon would sit approximately 28 inches from the surface of the basketball, about the distance from your elbow to the tips of your outstretched fingers. It is the first gap in our journey that the basketball model renders as something you can actually see: a ball the size of a tennis ball floating just over 2 feet from the basketball. When the Apollo astronauts left Earth orbit and aimed for the Moon, they traveled that 28 inches at a speed that took them approximately 3 days. 3 days of coasting through emptiness while Earth shrank behind them, and the grey cratered surface of the Moon grew slowly in the forward window. During those 3 days, they were farther from home than any human being had ever been. Radio signals between Mission Control in Houston and the spacecraft experienced a delay of 1.3 seconds each way. Ask a question, wait 1.3 seconds for it to arrive, Wait another 1.3 seconds for the reply to come back, a nearly 3-second round trip. That 1.3-second delay is the first crack in your intuition. You have spent your entire life with instantaneous communication. You pick up a phone and hear a voice as though the person were in the room beside you. You send a message, and it arrives before the muscle in your finger has relaxed from pressing the key. The idea that communication could have a delay, a real, physically unavoidable delay, is foreign to every experience your nervous system has accumulated. And yet, even at the distance of the moon, the fastest thing in the universe introduces a pause you can feel. This is the moon, the nearest object to Earth of any significance. The first rung on a ladder that climbs so far upward that what we have described so far, the ISS, the moon, the entire span of human exploration, will shortly become invisible. The next rung is 390 times farther away. The Sun sits at an average distance of approximately 93 million miles from Earth. Astronomers have a name for this distance, 1 astronomical unit, or AU. It is the standard unit of measurement for everything within the solar system, and it is going to get a lot of use in the next few minutes. 93 million miles. The number is available to you. Your brain reads it, notes it, and files it away without genuinely processing what it represents. So let us make it physical. If you drove a car to the Sun at 60 miles per hour, the speed you travel on a suburban highway without stopping for fuel, food, or sleep, the journey would take approximately 177 years. You would need to have begun driving before the American Civil War to be arriving now. Your great-great-great-grandparents would have set out on the journey. Every generation since would have continued it. You would be the first to arrive, and you would never have existed because no human lineage maintains 177 years of unbroken highway driving. A commercial jet traveling at 550 miles per hour would need about 19 years of continuous flight. Even light, the fastest thing in the universe, traveling at 670 million miles per hour, needs 8 minutes and 20 seconds to cover the distance from the Sun to the Earth. Every photon that lands on your skin right now, warming you, sustaining the photosynthesis that produced the food in your body, departed the Sun's surface before your morning cup of coffee finished brewing. You are perpetually living in the Sun's past. If the Sun vanished this instant, if every nuclear reaction in its core simply stopped, and it collapsed silently into darkness, you would continue to see it, continue to feel its warmth for another 8 minutes and 20 seconds before the last photon reached you and the sky went dark. 8 minutes of borrowed light. 8 minutes of a star that no longer existed. On our basketball model, 93 million miles places the Sun roughly 78 feet away. If you held the basketball at one end of a long corridor and walked 78 feet, about the length of a large house, you would be standing at the Sunday. The Sun itself at that scale would be a sphere about 8 inches across. A grapefruit 78 feet from a basketball, with an almost invisible grain of sand orbiting between them. That grain of sand is Earth. That is the entire theater of human civilization, a grain of sand orbiting a grapefruit 78 feet apart. The Sun is staggering in its own right. Its diameter stretches 8,640,000 miles. You could line up 109 Earths across its face. Its volume could contain approximately 1.3 million Earths. Every planet in the solar system, every moon, every asteroid, every comet, every grain of interplanetary dust adds up to roughly 0.14% of the solar system's total mass. The Sun accounts for the remaining 99.86%. Jupiter, the largest planet, a gas giant so immense it could swallow every other planet in the solar system simultaneously, is still roughly 1,000th. The mass of the Sunday Earth is less than a rounding error in the Sun's accounting. Yet the Sun's reach extends far beyond where any planet orbits. And this is where your intuition begins to fail completely. Mars orbits at an average of 1.5 AU, roughly 142 million miles from the Sunday. At its closest approach to Earth, the gap between the two planets shrinks to about 34 million miles. Even at that minimum distance, a radio signal traveling at the speed of light takes over 3 minutes to cross the void one way, 6 minutes round trip. You cannot have a conversation with anything on Mars. By the time your question arrives, and a reply could form and return to you 6 minutes have elapsed. The rover on the other end operates largely autonomously because real-time guidance from Earth is physically impossible. The distance has already made the speed of light feel slow. Jupiter orbits at 5.2 AU, Saturn at 9.5 AU. At Saturn's distance, sunlight has dimmed to approximately 1/100th of its intensity at Earth. A human standing on one of Saturn's moons would see the sun not as a blazing disk, but as an extraordinarily bright star, brilliant enough to cast shadows, but too small and distant to feel warm. The Cassini spacecraft, which orbited Saturn for 13 years before deliberately plunging into the planet's atmosphere in 2017, sent radio signals back to Earth that required between 67 and 85 minutes to arrive, depending on the orbital positions of the two planets. By the time data from Cassini's instruments appeared on scientists' screens in Pasadena, the spacecraft had moved thousands of miles from where it took the measurements. Uranus orbits at 19 AU. Neptune, the outermost recognized planet, orbits at approximately 30 AU. Light from the Sun needs over 4 hours to reach Neptune. The Voyager 2 spacecraft, which remains the only human-made object to have flown past Neptune, required 12 years of continuous flight to reach it after launch in 1977. 12 years of travel through mostly empty space to reach the outermost planet in our solar system. And even Neptune is nowhere near the true edge of the Sun's dominion. Beyond Neptune lies the Kuiper Belt, a disc-shaped region of icy bodies extending from about 30 to 50 AU. Beyond that, from roughly 50 AU outward, into the void, lies the scattered disk. And beyond that, far, far beyond that, lies the Oort cloud. The Oort cloud is the true outer boundary of the solar system, a vast theoretical shell of icy bodies believed to surround the Sun in a roughly spherical halo. Its inner edge sits at perhaps 2000 AU from the Sunday. Its outer edge may extend as far as 100000 AU, roughly 1.6 light-years from the Sunday. Objects in the outer Oort cloud are so weakly bound by the Sun's gravity that the gravitational nudge of a passing star or a gravitational ripple from the galactic disk can dislodge them, sending them falling inward on long elliptical paths. These are the long-period comets, visitors from the farthest suburbs of the solar system, taking tens of thousands or even millions of years to complete a single orbit. Now, consider Voyager 1. It launched in September 1977. As of 2026, it has been traveling for nearly half a century and has reached a distance of approximately 165 AU from the Sun, roughly 15 billion miles. It is the most distant human-made object ever built. In August 2012, it crossed the heliopause, the boundary where the Sun's solar wind gives way to the interstellar medium, becoming the first human artifact to enter the space between stars. 15 billion miles. 48 years of travel. The fastest object humanity has ever launched into the cosmos. At its current speed of roughly 38000 miles per hour, Voyager 1 would need approximately 500 years to reach the inner edge of the Oort cloud, 5 centuries, and it would then require a further 30000 years to pass through the cloud entirely and emerge on the other side. 30,000 years. The entirety of recorded human civilization, every city, every empire, every written word, every war, every scientific discovery, every work of art spans roughly 1,000,000 years. Voyager would need 3 times that entire span just to cross one structure within our own solar system. And here is the detail that collapses everything. The Oort cloud extends to approximately 1.6 light-years from the Sunday. The nearest star, Proxima Centauri, sits 4.24 light-years away. That means the true outer boundary of the solar system is less than halfway to the nearest neighbor. All of that, the planets, the Kuiper Belt, the scattered disk, the vast spherical shell of the Oort cloud, is contained within less than half the distance to the next star. On our basketball scale, the Sun is a grapefruit. Earth is a grain of sand 78 feet away. The Oort cloud extends outward for roughly 300 miles in every direction, and Proxima Centauri, the nearest neighboring grapefruit, sits approximately 750 miles away. 750 miles of absolute emptiness between two tiny spheres. That is interstellar space. That is what the neighborhood actually looks like. And all of this, the entire solar system, everything humanity has ever physically explored, every spacecraft ever launched, every signal ever sent, this is the smallest unit of measurement on the scale we are about to climb. The solar system is about to disappear, not shrink. Disappear. 4.24 light years. Those three words sit in the sentence without weight. Your eye passes over them the way it passes over a street address or a postal code. A piece of information noted, filed, moved past. The number is small enough to fit on a single line. The unit sounds familiar, and so the mind accepts it without resistance and continues on. But that unit, the light year, is doing all the work, and your mind is letting it pass unchallenged. 1 light year is the distance light travels in a single year. Light moves at 670 million miles per hour. In 1 second, a photon crosses approximately 186,000 miles, 7.5 times, around the entire circumference of the Earth. In 1 minute, it travels 11 million miles. In 1 hour, 670 million miles. In 1 day, roughly 16 billion miles. In 1 year, approximately 5.8 trillion miles. Multiply that by 4.24. The distance to Proxima Centauri, the absolute nearest star to our Sun, the closest pinprick of nuclear fire in the entire sky, is approximately 24.9 trillion miles. Written in full, that number requires 13 digits. It is a 2 followed by 12 zeros, give or take. And this is the nearest one. Everything else is farther. To feel what that distance means, physically return to the scale model. The Sun is a grapefruit. Earth is a grain of sand orbiting 78 feet away. The Oort cloud, the true outer shell of the solar system, extends 300 miles outward in every direction, and Proxima Centauri, the nearest neighboring grapefruit, sits roughly 750 miles away. 750 miles of absolute nothing between two tiny spheres. Now ask yourself, at Voyager 1's current speed of 38,000 miles per hour, how long would it take to cross those 24.9 trillion miles? The calculation is straightforward, and the answer is devastating. Approximately 73,000 years. Not decades, not centuries. 73,000 years. The last ice age ended roughly 11700 years ago. Voyager would need to travel for more than 6 ice ages laid end to end in sequence before it reached the nearest star, and it is not even aimed in that direction. Consider what humanity has done in 73,000 years. Modern humans emerged from Africa, migrated across continents, developed language, art, agriculture, cities, writing, mathematics, science, industry, built every civilization that has ever existed, composed every symphony ever heard, painted every canvas ever seen, fought every war ever recorded, generated every scientific insight ever published, and at the end of all that time, at the conclusion of the entire known span of modern human activity and achievement, Voyager would still be arriving. That is how far away the nearest star is. And yet the interstellar void between here and there is not simply emptiness in the way a vacant room is empty. It has a character, a texture, a physical reality that is worth understanding before we pass through it. Within the solar system, the Sun continuously pumps charged particles outward in all directions, a stream of electrons and protons called the solar wind. This wind fills the heliosphere, the bubble of solar influence, with a tenuous plasma that thins with distance but never entirely disappears until you reach the heliopause. Beyond that boundary in the interstellar medium, the environment changes. The solar wind drops away. The cosmic background radiation dominates, and the density of matter settles at roughly 1 atom per cubic centimeter. 1 atom per cubic centimeter. Your mind may not immediately register why that number matters, so consider the comparison. The air in the room where you are sitting right now contains approximately 27 quintillion molecules per cubic centimeter, that is 27, followed by 18 zeros. The interstellar medium contains 1 atom per cubic centimeter. The ratio between those two numbers is so extreme that interstellar space qualifies as a more perfect vacuum than anything ever produced in a laboratory on Earth. The best vacuum chambers ever built, cooled to near absolute zero, and pumped down with the most powerful equipment available, still contain more particles per cubic centimeter than the space between stars. If you could somehow be transported instantaneously to a point halfway between the Sun and Proxima Centauri and deposited there unprotected without a suit, you would not experience cold the way you experience winter. Cold implies the transfer of heat from your body to a surrounding medium. In interstellar space, there is almost no medium to transfer heat to. What you would experience instead is a different kind of death, the slow boiling of your blood into vacuum as the pressure around you dropped to nothing, and simultaneously the freezing of your outer tissues as thermal radiation carried heat away from your body into a void with no mechanism to return. The temperature of the interstellar medium in our region of the galaxy runs between roughly 6000 and 10000 degrees Kelvin in the warm ionized phase, but that temperature is a measure of individual particle velocities, not of thermal energy transfer. With so few particles present, almost no heat would actually reach your body. You would be surrounded by technically hot particles and simultaneously freeze to death. The void has a paradoxical physics that ordinary language was not built to describe. This emptiness is not featureless. Vast clouds of molecular hydrogen drift between the stars, some stretching dozens of light years across. These molecular clouds are stellar nurseries regions, where gas slowly accumulates under its own gravity until pockets of it become dense enough to collapse heat up from compression and ignite nuclear fusion in their cores. Every star you have ever seen in the night sky was born inside one of these clouds. The Sun itself formed roughly 4.6 billion years ago from a collapsing region within a molecular cloud that no longer exists, consumed by the star formation it triggered. But here is the fact about interstellar space that stops being poetry the moment you think it through carefully enough. The material that became Earth, that became you, was once part of that interstellar medium. Not in any vague or approximate sense, literally, physically, atomically. The iron in your blood was fused in the core of a massive star that, exhausted its nuclear fuel, collapsed and exploded as a supernova billions of years before the Sun was born. The calcium in your bones was produced by a different type of stellar explosion. The oxygen filling your lungs with every breath was forged inside the nuclear furnace of yet another star that lived and died long before our solar system existed. The carbon that forms the backbone of every biological molecule in your body was assembled in the dying atmosphere of a red giant star that shed its outer layers into space as a planetary nebula. These are not metaphors, they are chemistry. They are nuclear physics. The atoms in your body carry isotopic signatures, specific ratios of different atomic variants that record the history of their stellar origins, the way tree rings record the history of a tree's growth. Astronomers can read those signatures. They have read them, and what those signatures say is that you are not made of Earth, you are made of the galaxy. Your body is a temporary arrangement of atoms that have spent most of their existence drifting through interstellar space between stars that no longer exist, waiting across billions of years and billions of miles to be gathered by gravity into a molecular cloud, into a collapsing protostellar disk, into a rocky planet, into an ocean, into a cell, into you. The void between stars is not wasted space. It is the medium through which the galaxy redistributes the products of stellar nucleosynthesis. It is the slow river along which the raw materials of planets and people are transported across light years and geological epochs. Every atom that was ever part of a living thing was once part of that river. Now step back and look at the river's banks. The Milky Way galaxy contains an estimated 200 to 400 billion stars. The uncertainty in that number is itself staggering. We cannot count our own galaxy's stars directly because we are embedded inside it, surrounded by dust clouds that block visible light across most of the galactic disk. What we can do is measure the galaxy's total luminosity, model its stellar mass function, and use infrared observations that penetrate the dust to count stars in representative samples. The result converges on a population between 200 and 400 billion, with most recent analyses favoring the higher end, 200 to 400 billion stars. Each one a nuclear furnace, each one potentially surrounded by its own retinue of planets, and each one separated from its nearest neighbors by distances so vast that Voyager 1, traveling for 48 years at 380,000 miles per hour, has not covered even 0.1% of the distance to the nearest one. The population of stars within that number is not uniform. It is a zoo of physical extremes, and the variety hidden inside those 400 billion furnaces is worth pausing on before we try to comprehend the galaxy as a whole. The most common stars in the Milky Way are red dwarfs, accounting for roughly 70 to 75% of the entire stellar population. They are small, cool, and dim, with surface temperatures ranging from about 3000 to 4000 degrees Kelvin and masses as low as 8% of the Sun's. The smallest red dwarfs generate so little heat that a planet would need to orbit extremely close to remain warm enough for liquid water, so close that gravitational forces would likely lock one face of the planet permanently toward the star, leaving one hemisphere in eternal daylight and the other in permanent night. What red dwarfs lack in brilliance, they compensate for in longevity. A red dwarf burns its hydrogen fuel so slowly, so patiently, so conservatively that it can shine for trillions of years, far longer than the current age of the universe. The universe is 13.8 billion years old. The longest-lived red dwarfs will continue burning for 10 trillion years or more. This means something remarkable. Every red dwarf that has ever ignited is still burning today. Not one has had time to die. The galaxy's most numerous stars are all still in their infancy, and almost none of them are visible to the naked eye. The night sky you see from a dark field is dominated by rare luminous giants. The true population of the galaxy hides in the dark, invisible to unaided human eyes, patient beyond any timescale our civilization has existed long enough to contemplate. At the opposite extreme sit the blue supergiant stars, so massive and so hot that they burn through their nuclear fuel in just a few million years. A blue supergiant can contain 50 to 100 times the mass of the Sun, with surface temperatures exceeding 300,000 degrees Kelvin and luminosities outshining the Sun by factors of hundreds of thousands. A single blue supergiant radiates more energy per second than an entire cluster of red dwarfs produces across a full year. But their ferocity is their undoing. These stars live fast, fusing hydrogen into helium, helium into carbon, carbon into oxygen, oxygen into silicon, silicon into iron, each successive fuel burning faster and hotter than the last. When iron accumulates in the core, nuclear fusion can no longer release energy. The reactions stop. In less than a second, the core collapses under its own gravity, compressing a mass greater than the Sun into a sphere roughly 12 miles across. The outer layers, suddenly unsupported, fall inward and then rebound. The resulting explosion, a core collapse supernova, briefly releases more energy than the Sun will emit across its entire 10 billion year lifetime. For a few weeks, a single dying star can outshine an entire galaxy of hundreds of billions of suns. What remains depends on the mass of the original star. Some leave behind neutron stars, objects so dense that a single teaspoon of their material would weigh roughly 6 billion tons on Earth's surface. Their gravity is so intense that the protons and electrons in ordinary matter are compressed together into neutrons, producing a crystal of nuclear matter harder than any substance that exists in ordinary physics. Some neutron stars spin hundreds of times per second, sweeping beams of radio waves across space like cosmic lighthouses. These are pulsars, and their timing is so precise, so metronomically regular, that the first astronomers to detect one in 1967 briefly considered whether the signal might be artificial. They labeled the source LGM1, Little Green Men. It was not. It was a dead star spinning 30 times per second, announcing its existence to the cosmos through pure rotational momentum. The most massive dying stars leave behind something else entirely. When the core of a star, more than roughly 20 to 25 times the mass of the Sun, collapses, not even the pressure of neutron degeneracy can halt the implosion. The core continues collapsing past neutron star density, crushing itself into a mathematical singularity, a point where the known equations of physics reach their limits and stop providing answers. Surrounding this point at a distance called the Schwarzschild radius, space-time curves so severely that the escape velocity exceeds the speed of light. Nothing that crosses that boundary returns. Not matter, not radiation, not information of any kind. This region is a black hole. The Milky Way is estimated to contain between 100 million and 1 billion stellar mass black holes, the collapsed remnants of massive stars that lived and died across the galaxy's 1.3 billion year history. They drift through the galactic disk and halo, invisible in isolation, detectable only when they interact with nearby matter, or reveal themselves through their gravitational influence on surrounding objects. You could pass within a few light years of a stellar mass black hole and never know it was there. It would emit no light. It would make no sound. It would simply curve the paths of passing photons, slightly producing a faint distortion in the background star field that no unaided human eye could detect. At the very center of the Milky Way sits something far larger. Sagittarius A star is a supermassive black hole with a mass of approximately 4 million times that of the Sun, compressed into a region smaller than the orbit of Mercury. Its existence was established through decades of painstaking observation by astronomers tracking individual stars near the galactic center, most notably the work of Andrea Ghez at UCLA and Reinhard Genzel at the Max Planck Institute, work that earned them the Nobel Prize in Physics in Laniakea. One of those stars, designated S2, orbits Sagittarius A star with a period of roughly 16 years. At its closest approach, S2 reaches a speed of approximately 2.7% of the speed of light, fast enough that relativistic effects become measurable and must be accounted for. The only object capable of producing those orbital velocities without being visible is a black hole of the mass astronomers calculated. In 2022, the Event Horizon Telescope Collaboration, a global network of radio telescopes operating as a single Earth-sized instrument, released the first direct image of Sagittarius A star itself, a glowing ring of superheated gas swirling around a dark central shadow, exactly as Einstein's equations of general relativity predicted a century earlier. The monster at the center of our galaxy is real. It has been photographed. Despite its 4 million solar mass bulk, Sagittarius A star is surprisingly quiet by the standards of supermassive black holes. In many other galaxies, the central black hole is actively consuming material at a prodigious rate, producing jets of plasma that extend hundreds of thousands of light years and outshining every star in the host galaxy combined. These are quasars, the most luminous sustained objects in the universe, and they can be observed across billions of light years of cosmic distance. Sagittarius A star, by comparison, is nearly dormant. It consumes very little material in its current state, but it has not always been this quiet. Enormous structures called the Fermi bubbles, 2 lobes of high-energy gas, extending roughly 25000 light-years above and below the galactic plane, record the evidence of past violence. These bubbles were likely produced by a period of intense activity in Sagittarius A star several million years ago, when the black hole was consuming material at a much higher rate and blasting jets of energy into the surrounding medium. The galaxy's center was once a quasar, or something close to one. Now it sleeps, but the scars of its active phase still glow in gamma-ray wavelengths, visible to instruments like NASA's Fermi Gamma-Ray Space Telescope. The monster is resting. It has not always rested. Now pull back from the center and look at the galaxy as a whole. The Milky Way is a barred spiral galaxy, a flattened disk of stars, gas, and dust, organized into a pattern of sweeping spiral arms emerging from a central bar-shaped region of older stars. Its luminous disk spans roughly 1,000,000 light-years in diameter and approximately 2,000 light-years in thickness. At the Sun's position, Though it flares and thickens at the edges, the proportions are worth absorbing. The disk's diameter, compared to its thickness, is roughly the same as a compact disk compared to its thickness. If you scaled the Milky Way to the size of a dinner plate, the entire stellar disk would be thinner than a sheet of paper. The Sun orbits the galactic center at a distance of approximately 2,600,000 light-years, placing it roughly halfway between the core and the outer edge of the visible disk. We sit within a minor spiral structure called the Orion Arm, sometimes called the local spur, positioned between two larger arms, the Perseus Arm and the Sagittarius Arm. Our position in the galaxy is neither central nor peripheral, it is suburban. A quiet, residential zone where stars are spaced a few light-years apart, and the environment is calm enough for a stable planetary system to have persisted for 4.6 billion years. The Sun moves. At roughly 515,000 miles per hour, about 143 miles per second, the Sun orbits the galactic center in a path that takes approximately 230 million years to complete. Astronomers call this period a galactic year or a cosmic year. The last time the Sun was at its current position in its orbit, the Triassic period was just ending on Earth. Dinosaurs had not yet appeared. The time before that, the most complex life on the planet consisted of early fish and primitive land plants. In the entire 4.6 billion-year history of the solar system, the Sun has completed only about 20 galactic orbits, 20 laps around a galaxy in 4.6 billion years. Surrounding all of this visible structure, surrounding the glowing disk of spiral arms, surrounding the dense central bulge, surrounding even the faint outer reaches of the stellar halo, sits a vast invisible mass that makes everything we can see irrelevant by comparison. Dark matter, a substance that does not emit light, does not absorb light, does not interact with electromagnetic radiation in any way currently detectable. Its presence is known only through its gravitational effects. The evidence is unambiguous and has been accumulating for decades. Stars in the outer regions of galaxies orbit faster than they should, given only the visible mass of the stars and gas inside their orbits. If you apply Newton's law of gravity to what you can see, the outer stars should be moving much more slowly enough, in fact, that they should have escaped the galaxy's gravitational hold billions of years ago. They have not escaped. They are still there, still orbiting, still bound. Something is holding them, something massive, something invisible, something distributed in a vast spherical halo, extending far beyond the visible disk. That something is dark matter, and in the Milky Way, it accounts for roughly 85% of the total mass. The total mass of the Milky Way, including stars, gas, dust, and dark matter, is estimated at approximately 1.5 trillion solar masses. The visible stars and gas that fill astronomy photographs the brilliant spiral arms that make the galaxy recognizable account for perhaps 150 to 200 billion solar masses of that total. Everything you can see, every photon emitted by every star in the galaxy represents roughly 10 to 15% of what is actually there. The Milky Way is mostly invisible, and the dark matter halo extends far beyond the luminous disk. Where the visible galaxy ends, where the spiral arms thin out, and the density of stars drops toward the background, the dark matter continues outward. Current estimates place the dark matter halo's radius at somewhere between 3,000,000 and 1 million light-years. The part of the Milky Way that glows, that we can photograph and study and celebrate, is a thin, bright ember embedded in the center of an invisible gravitational structure, roughly 5 to 10 times larger in every direction. The galaxy you think of when you hear the word galaxy is the frosting on an invisible cake that outweighs it by a factor of 10. 400 billion stars. A central black hole 4 million times the mass of the Sunday. A dark matter halo extending perhaps 1 million light-years in every direction. A disk so flat relative to its width that it would be thinner than paper at dinner plate scale. A rotational period of 230 million years. An age of approximately 13.6 billion years, nearly as old as the universe itself. This is the Milky Way. This is home. and home is about to become a single point of light, because the Milky Way, this colossal structure that has consumed an entire chapter of our journey, this galaxy so vast that light needs 1,000,000 years to cross its luminous disk, this system of 400 billion stars held together by 1.5 trillion solar masses of matter, visible and invisible, is one of more than 80 galaxies in a gravitationally bound family called the local group, and the local group itself is a minor suburb of something larger still. The galaxy is not the last scale. It is not even close to the last scale. It is the next thing to disappear. 1652, Claude responded. The nearest galaxy of any significance to the Milky Way is not a small thing. The nearest galaxy of any significance to the Milky Way is not a small thing. Andromeda, catalogued by astronomers as Messier 31, is a spiral galaxy broadly comparable to our own. It contains somewhere between 1 trillion and 1.5 trillion stars, making it somewhat more massive than the Milky Way by most current estimates. It has its own central supermassive black hole, its own system of satellite galaxies, its own dark matter halo, extending hundreds of thousands of light years into the intergalactic void. It is by any reasonable standard an enormous and complex structure. It sits approximately 2.5 million light years away. That number deserves its own moment of stillness before we continue. 2.5 million light years. The light that left Andromeda and is entering your eye right now, if you were outside on a clear dark night and looking in the right direction, began its journey 2.5 million years ago. At that moment, the ancestors of modern humans were just beginning to chip stone tools on the plains of eastern Africa. Homo sapiens did not exist. Language did not exist. Fire had not yet been controlled. Agriculture was 2.49 million years in the future. Every human being who has ever lived, every civilization that has ever risen and fallen, every thought ever thought by a member of our species, falls within the last fraction of 1% of that photon's journey. You are not seeing Andromeda as it is. You are seeing a ghost, a portrait painted in ancient light, a record of a galaxy as it appeared before your species existed. By the time that image reaches your retina, 2.5 million years of Andromeda's history have occurred that you cannot see and will never see, because the light carrying that information has not yet arrived. Every time you look at Andromeda, you are doing archaeology. The gap between the Milky Way and Andromeda is not merely large, it is qualitatively different from the distances we have discussed so far. The space between planets is the solar system's interior. It is still, loosely speaking, solar space, filled with the sun's wind and the sun's gravitational authority. The space between stars is the interstellar medium, cold, nearly empty, but still part of the galaxy's structure, threaded with magnetic fields and wisps of gas and the gravitational web of stellar motion. But the space between the Milky Way and Andromeda is intergalactic space. It belongs to neither galaxy. It is a genuine... The density of matter in the intergalactic medium between the local group galaxies sits at roughly 1 to 10 atoms per cubic meter, not per cubic centimeter, per cubic meter. The interstellar medium within the Milky Way holds roughly 1 million atoms per cubic centimeter, which itself is already a vacuum, more perfect than anything producible in a laboratory. The intergalactic medium is 1 million times emptier than that, 1 billion times emptier than the air in this room. If you were somehow placed in the void between the Milky Way and Andromeda, the nearest atom of ordinary matter would be on average roughly 1 meter away from the nearest other atom. You would be surrounded by a perfection of emptiness that has no analogue in any human experience or any human technology. The temperature of that void hovers just above 2.7 degrees, Kelvin barely above absolute zero, the temperature floor set by the cosmic microwave background radiation that permeates all of space. No star close enough to warm you, no galaxy close enough to see with naked eyes. Total darkness, total silence, total isolation. And yet even across that gulf, the Milky Way and Andromeda are falling toward each other. Not drifting, not wandering in the same general direction. Falling, they are locked in a mutual gravitational embrace that has been pulling them together for billions of years. Andromeda is approaching the Milky Way at approximately 250,000 miles per hour, closing the 2.5 million light-year gap with the patience of cosmic time. In approximately 4 to 5 billion years, the two galaxies will collide. The word collision requires unpacking because it does not mean what it implies. When two galaxies collide, individual stars almost never strike each other. The stars within each galaxy are separated by distances so vast, an average of several light-years between neighbors, that even when two galaxies fully interpenetrate, the probability of any two individual stars making direct contact extraordinarily small. The collision is gravitational, not physical. The two galaxies will pass through each other like two clouds of smoke, their gravitational fields interacting and distorting, pulling stars into new orbits, stretching the spiral arms into long tidal streamers, triggering enormous bursts of star formation as gas clouds are compressed and destabilized by this encounter. The collision will unfold across roughly 1 billion years, a slow-motion catastrophe visible only on timescales that dwarf all of recorded history. Computer simulations of the merger, run by teams at NASA and multiple research institutions, predict that the Sun will likely survive, flung into a new orbit around the combined system, probably at a significantly larger distance from the emerged center than it currently sits. Earth, if it still exists, will probably survive as well, carried along with the Sun into its new trajectory. The night sky, however, will be transformed beyond recognition. Stars that are currently invisible to the naked eye will become bright neighbors. The structure of the combined galaxy will reorganize over hundreds of millions of years into a new form, likely a giant elliptical galaxy, smooth and featureless, lacking the ordered spiral arms of its progenitors. Astronomers have already given this future galaxy a name, Milky Way. The monster created by the merger will harbor two supermassive black holes, the 4 million solar mass remnant of Sagittarius A star, and whatever mass Andromeda's central black hole currently holds. Over time, those two black holes will spiral toward each other through the combined galactic center, losing energy through the gravitational radiation predicted by general relativity, until they eventually merge in an event that will release more energy in gravitational waves than the combined luminosity of every star in the new galaxy. A collision of galaxies, a merger of monsters, and on the scale of what surrounds the local group, this event will be entirely unremarkable. A minor rearrangement of furniture in a single room of a structure that contains millions of rooms. The local group is the gravitationally bound collection of galaxies, of which the Milky Way and Andromeda are the two dominant members. It contains more than 80 known galaxies, spread across a volume roughly 10 million light-years in diameter. Most of its members are dwarf galaxies, faint small structures containing between a few million and a few billion stars each. The triangulum galaxy Messier 33 is the third largest member, containing roughly 40 billion stars and sitting approximately 3 million light-years from the Milky Way. The Large Magellanic Cloud holds perhaps 30 billion stars, the Small Magellanic Cloud roughly 7 billion. Many of the other members are so faint and small that they were not discovered until modern deep sky surveys began revealing them hiding in the Milky Way's glare. 10 million light-years, 80 galaxies, anchored by the mutual gravity of the Milky Way and Andromeda, with the remaining members orbiting around the common center of mass of the two dominant galaxies like moons around twin planets. Everything within the local group is gravitationally bound to everything else. It is a real physical structure, a genuine community, a cosmic household in which the members are permanently linked. It is also an almost invisibly small smudge on the next scale up. The Virgo cluster sits approximately 54 million light-years from the local group. It contains more than 1,300 known galaxies, nearly 20 times the membership of the local group, concentrated into a volume roughly 15 million light-years across. Its total mass, including dark matter, is estimated at approximately 1.2 quadrillion solar masses, written in scientific notation 1.2 times 10 to the 15th power suns. At the heart of the Virgo cluster sits a giant elliptical galaxy called Messier 87, which harbors a supermassive black hole with a mass of 6.5 billion solar masses, more than 1,000 times the mass of the black hole at the center of the Milky Way. That black hole became famous in 2019 when the Event Horizon Telescope collaboration released the first direct image of a black hole in history. The glowing orange ring of superheated plasma swirling around the shadow of Messier, Otyuhus Central Monster. That image traveled 54 million light-years to reach us. The light captured in that photograph was emitted when the earliest ancestors of modern horses were appearing on Earth. Every primate species that has ever existed, every hominid lineage, the entire human story fits within the last fraction of that light's journey. 54 million light-years, the distance to the nearest major galaxy cluster. And already the local group with its 10 million light-year diameter, its 80 galaxies, its impending merger of 2 trillion star systems, has become a minor peripheral feature of the larger structure. A small suburb on the outskirts of something vastly more significant. The local group is falling toward the Virgo cluster. All of it, the Milky Way, Andromeda, the Triangulum galaxy, the Magellanic Clouds, every dwarf satellite galaxy in the family is being pulled toward Virgo at roughly 400 kilometers per second. But the expansion of the universe is carrying the Virgo cluster away from us, slightly faster than we are falling toward it, so the gap between us and Virgo is slowly growing despite our motion in its direction. We will never reach it. We are falling towards something we will never arrive at, pulled by a gravity we cannot overcome, and simultaneously swept away by an expansion we did not choose and cannot stop. The gravitational influence of the Virgo cluster, however, is real and measurable. It distorts the motion of every galaxy in our region of space, adding a systematic drift that astronomers must carefully account for when measuring cosmic velocities. The Virgo cluster's gravity reaches across 54 million light-years and tugs on the Milky Way with a force that over cosmic time would have pulled us significantly from where we would otherwise be. The cluster we will never reach has already shaped our trajectory, but neither the local group nor the Virgo cluster exist in isolation. Both are embedded within a far larger gravitational structure that was only definitively identified and named in 2014 when astronomer Brent Tully and his colleagues published a landmark paper in the journal Nature, mapping the boundaries of what they called Laniakea. The name comes from Hawaiian. It means immeasurable heaven. Laniakea is a supercluster, a collection of galaxy groups and clusters bound together within a single coherent gravitational drainage basin. It spans approximately 500 million light-years and contains the mass of roughly 100 million billion suns distributed across an estimated 1,000,000 galaxies. The Milky Way, the local group, the Virgo cluster, all are members of Laniakea. All are falling along with tens of thousands of other galaxies toward a single gravitational focal point within the supercluster called the Great Attractor. The Great Attractor is a concentration of mass partially hidden behind the densest part of the Milky Way's own disk, the region astronomers call the zone of avoidance, where our own galaxy's dust and stars obscure the view of anything beyond. For decades after it was first inferred from galaxy motion patterns in the 1970s and 1980s, the Great Attractor was a mystery, a gravitational source pulling hundreds of thousands of galaxies toward it, located precisely in the direction that was hardest to observe. Using X-ray and infrared wavelengths that penetrate the galactic dust, astronomers eventually identified the source, a massive supercluster region centered on the Norma cluster, approximately 250 million light-years away. Everything within Laniakea is falling toward it. The Milky Way, Andromeda, the Virgo cluster, every galaxy in the local group. Every galaxy in every group and cluster throughout the supercluster's 500 million light-year extent. All of them flowing like water draining toward a basin drawn by the combined gravitational pull of one of the densest concentrations of matter in our region of the universe. 500 million light-years. To feel what that distance means in time-light, leaving one edge of Laniakea and traveling toward the other edge would need 500 million years to make the crossing. When that light departed, the most complex life on Earth consisted of simple marine animals. The Cambrian explosion, the sudden diversification of multicellular animal life that produced most of the major body plans that still exist today, had not yet occurred. Fish had not evolved. Insects did not exist. Reptiles did not exist. Mammals did not exist. The entire vertebrate lineage had not yet appeared. Every creature that has ever walked, flown, swum, or crawled on this planet arose, diversified, dominated, and in many cases went extinct during the time it takes a single photon to cross the supercluster we inhabit. And Laniakea itself is one supercluster among hundreds of millions in the observable universe. Adjacent to Laniakea lies the Perseus-Pisces supercluster, one of the most prominent, large-scale structures in the local universe. The Shapley supercluster, the most massive concentration of galaxies within 1 billion light-years of Earth, sits roughly 650 million light-years away and exerts its own enormous gravitational influence. Laniakea itself may be falling toward Shapley as part of an even larger flow pattern that astronomers are still working to map and understand. The hierarchy of gravitational structures does not stop at superclusters. It continues upward into something larger still. Step back far enough that Laniakea itself is a small feature in the view, and something extraordinary reveals itself. Matter in the universe is not distributed randomly. It is not scattered uniformly through space like dust on a still surface. It is organized, arranged into a vast, interconnected network of structures that spans the entire observable universe. Scientists call it the cosmic web. The cosmic web is the largest scale organization of matter that exists. If you could somehow observe the entire observable universe from outside, if you could hold all 93 billion light-years of it in a single field of view, you would see a structure unlike anything your eyes have encountered. Not a cloud, not a scatter of points, a web, a three-dimensional lattice of filaments, sheets, nodes, and voids, resembling simultaneously the structure of a sponge, the neural architecture of a brain, the tracery of foam on the surface of water, and the branching pattern of lightning frozen in glass. The cosmic web is composed of 4 distinct structural elements. Nodes are the densest regions, the intersections where multiple filaments converge. Galaxy clusters and superclusters form at these nodes, anchored by the deepest gravitational wells in the universe. The Virgo cluster is a node. The Norma cluster at the heart of the Great Attractor is a node. Every massive galaxy cluster you have ever seen photographed sits at one of these convergence points. Filaments are the great connective threads of the web, long narrow bridges of dark matter and gas stretching between nodes, sometimes spanning hundreds of millions of light-years while maintaining widths of only 10 to 20 million light-years. Galaxies form preferentially along these filaments, strung out like beads on a string, their formation triggered by the slightly elevated density of gas and dark matter within the filament structure. The filaments are the highways of the cosmos. Matter flows along them, funneled by gravity toward the nodes where it accumulates into clusters. Walls are vast sheet-like surfaces where multiple filaments intersect broad planar structures containing thousands of galaxies arranged in thin layers extending across hundreds of millions of light-years. The Sloan Great Wall, mapped through the Sloan Digital Sky Survey, stretches approximately 1.4 billion light-years across, making it one of the largest known coherent structures in the universe, a single sheet of galaxies spanning more than 1 billion light-years of space. And between all of these, between the nodes and the filaments and the walls, lie the voids. The voids are the dominant feature of the universe by volume. They are enormous, nearly spherical regions of space that are almost entirely empty of galaxies. Typical voids span between 100 and 500 million light-years across. They are not completely empty. Dark matter exists within them at reduced density, and the faintest wisps of intergalactic gas thread through their interiors, but they contain almost nothing of what astronomers would call significant structure. No clusters, no major galaxies, almost no stars. The Boötes void, discovered in 1981, stretches approximately 330 million light-years in diameter. If the Milky Way sat at its center, the nearest large galaxy would be so distant it would appear as a faint smudge detectable only through a powerful telescope. The night sky from inside a void would be vastly emptier than what we see from our position in the cosmic web, a darkness so profound that ancient astronomers, had they inhabited such a world, might have concluded that the universe contained almost nothing. Voids occupy roughly 80% of the universe's total volume. Consider that for a moment. 80% of all the space in the observable universe is void, nearly empty, nearly featureless, nearly structureless. The nodes, filaments, and walls, all the galaxies, all the clusters, all the superclusters, all the structures we have named and mapped and photographed, occupy the remaining 20%. The universe is overwhelmingly composed of nothing, with complexity confined to a thin tracery of connected structures, threading through an ocean of emptiness. We live in that tracery. On a planet orbiting a star inside a galaxy, inside a supercluster, threaded along a filament of the cosmic web, the fraction of the universe's volume we inhabit is not merely small, it is among the most structurally complex, gravitationally dense, cosmologically active regions of space that exists. We live in the foam, not the air inside the bubbles. The origin of the cosmic web traces back to the first moments of existence, to events that occurred within the first fraction of a second after the Big Bang, in a period called cosmic inflation. During inflation, quantum fluctuations in the density of the primordial plasma variations, so tiny they existed at the subatomic scale, were stretched by the exponential expansion of space to macroscopic and eventually cosmic scales. These fluctuations were extraordinarily subtle. Regions of slightly higher density differed from regions of slightly lower density by roughly 1 part in 1,000,000. 1 part in 1,000,000. That is the seed of everything you see in the night sky. In the 13.8 billion years since inflation, gravity has been amplifying those initial fluctuations. Regions that started with slightly more density attracted slightly more matter, which increased their density further, which attracted still more matter. Regions that started with slightly less density lost matter to their denser neighbors, emptying further and further over time. The process compounded across billions of years into the structures we observe today. Galaxy clusters at the densest nodes, enormous voids at the least dense regions, and the entire filigree of filaments and walls threading between them. The cosmic web is gravity's autobiography, the record of 13.8 billion years of gravitational amplification acting on quantum noise. Every filament traces a line of slightly higher primordial density. Every void marks a region that started with marginally less matter than its surroundings. The largest structures in the observable universe grew from fluctuations smaller than an atomic nucleus. The evidence for this origin story is written across the entire sky, in a form that can be detected with the right instruments. The cosmic microwave background radiation, the ancient light released when the universe was just 38,000,000 years old and the first stable atoms were forming, carries the imprint of those primordial fluctuations as faint temperature variations across the sky. Satellites including COBE, WMAP, and most recently, Planck have mapped those temperature variations with extraordinary precision, revealing the seeds of all future cosmic structure in a pattern of tiny hot and cold spots spread across the entire celestial sphere. The patterns match. Feed those observed temperature variations into a supercomputer simulation that models how gravity, dark matter, dark energy, and ordinary matter evolve over 13.8 billion years, and the simulation produces a cosmic web that matches the observed one with impressive fidelity. Filaments appear at the right scales, voids open at the right sizes, clusters assemble at the nodes with the right masses and temperatures. The agreement between the quantum fingerprints in the cosmic microwave background and the large-scale structure of the universe today is one of the great triumphs of modern cosmology. We understand in broad strokes why the universe looks the way it does. We can trace the origin of the largest structures in existence back to the smallest fluctuations physics allows. The cosmic web is not mysterious in its cause. It is the inevitable product of known physics, operating over known timescales on known initial conditions. What remains mysterious is what those initial conditions ultimately came from. What caused inflation? What set the specific values of the quantum fluctuations? what determined the ratio of dark matter to ordinary matter to dark energy that shaped everything that followed. These questions sit at the frontier of theoretical physics unanswered, resisting every approach that has been tried. The web, whose origin we partially understand, remains rooted in a beginning we do not. In early 2025, an international team using the MUSE instrument on the European Southern Observatory's Very Large Telescope published the first high-definition image of a cosmic web filament connecting two galaxies at a distance corresponding to when the universe was roughly 2 billion years old. The filament stretched approximately 3 million light-years, and for the first time, researchers could directly trace the boundary between gas residing inside galaxies and gas flowing through the cosmic web itself. When compared to state-of-the-art supercomputer simulations of cosmic structure, the observed filament matched theoretical predictions with remarkable precision. The cosmic web, long inferred from the statistical distribution of galaxies and predicted by simulation, had finally been directly seen. The Euclid Space Telescope launched in July 2023, and releasing its first major data in 2025, is building the most ambitious map of cosmic structure ever attempted, surveying a third of the entire sky, measuring the shapes, positions of billions of galaxies across 10 billion years of cosmic time, and constructing a three-dimensional map of how dark matter is distributed across the universe's history. Its early results already show the cosmic web's filamentary structure with a clarity and depth never before achieved. When its full data set is released in the coming years, it will provide the most detailed picture ever assembled of how the web grew from its quantum seeds into the structure that fills the observable universe today. Now stand at the summit of what we have climbed and look back down. You began as a 6-foot figure on the surface of a planet 8,000 miles across. You crossed to the moon at 238,900 miles. You traveled to the sun at 93 million miles. You crossed the solar system to the edge of the Oort cloud at roughly 1.6 light-years. You crossed interstellar space to the nearest star at 4.24 light-years. You mapped the Milky Way at 1,000,000 light-years across. You stepped to Andromeda at 2.5 million light-years. You surveyed the local group at 10 million light-years. You crossed to the Virgo cluster at 54 million light-years. You traversed Laniakea at 500 million light-years. And now, the cosmic web stretches before you in every direction, filaments and voids and walls and nodes extending for billions of light-years, organized into patterns so immense that individual superclusters are minor features within them. At every step, the same thing happened. The scale you had just absorbed, the one that felt enormous, the one that had taken all of your mental effort to hold, was revealed to be invisible inside the next one. The solar system vanished inside the galaxy. The galaxy vanished inside the local group. The local group vanished inside Laniakea. Laniakea is disappearing inside the cosmic web. Each frame of reference you adopted was swallowed whole by the next frame. Nothing survived. The transition unchanged. Every largest thing became a rounding error. And the cosmic web, all of it, every filament and void and cluster and supercluster, is contained within a single sphere. That sphere has a name, and the number that describes it is about to make everything we have discussed collapse into a single point of ancient light. "Il woo-woo," Claude responded. "The observable universe has a diameter of approximately 93 billion light-years. The observable universe has a diameter of approximately 93 billion light-years. That sentence contains one of the most commonly misunderstood numbers in all of science, and it deserves careful unpacking before we go any further. Because if you have been paying attention, you may have already noticed something that does not add up. The universe is 13.8 billion years old. Light travels at a fixed speed. So, the farthest anything could possibly be the maximum distance any photon could have traveled since the beginning of time should be 13.8 billion light-years. And yet the number is 93 billion. The discrepancy is not an error. It is not an approximation. It is the consequence of a fact about the universe so fundamental and so strange that even physicists needed decades to fully absorb its implications. Space itself expands, not matter moving through space. Space, the fabric of distance itself, stretching, growing, carrying everything embedded within it outward in every direction simultaneously. In the first moments after the Big Bang, this expansion was almost incomprehensibly rapid. During the epoch called cosmic inflation, the universe expanded by a factor of at least 10 to the 26th power, that is a 1 followed by 26 zeros, in a time so brief it makes a nanosecond seem geological. What was once smaller than a proton became, in an instant, measured in fractions of a second, a volume large enough to eventually produce the observable universe we inhabit. After inflation, the expansion slowed, but it never stopped. It has been going on ever since. It is happening right now at this moment as you read these words. Here is what that means for the number 93 billion. When the universe was 3,800,000 years old, the moment the cosmic microwave background radiation was released, the earliest light we can observe, the regions that emitted that light were located at that time roughly 42 million light years from what would eventually become Earth. Not 13.8 billion light years, 42 million. That light has been traveling toward us ever since for 13.8 billion years. But while it was traveling, the universe was expanding, carrying its point of origin farther and farther away. By the time that ancient light finally reached our instruments, the region that emitted it had been swept outward by the expansion of space to a current distance of approximately 46 billion light years. Double that for the opposite direction and you get 93 billion light years, the full diameter of the observable universe. The observable universe is not 13.8 billion light years across, because space does not stand still while light travels through it. Space expands. Light chases a moving target, and the target has been moving for 13.8 billion years, at speeds that in the early universe exceeded the speed of light. Not because anything moved faster than light through space, but because space itself was expanding faster than light could cross it. This is the universe we can see. Everything within this 93 billion light-year sphere is in principle observable. Its light has had enough time to reach us, accounting for the expansion. Everything outside this sphere is for now beyond our observational reach. Not because it does not exist, because its light has not yet arrived. The observable universe is not the whole universe. It is the portion of the universe that is currently visible from our location in space and time. Within that sphere, current estimates place the total number of galaxies at approximately 2 trillion. 2 trillion galaxies. The revision of that number from an earlier estimate of roughly 200 billion to the current figure of 2 trillion came in 2016 when a team led by astronomer Christopher Consolis at the University of Nottingham combined data from the Hubble Space Telescope with mathematical modeling, of galaxy populations, too faint and small to be directly detected. Their analysis concluded that the observable universe contains roughly 10 times more galaxies than previous surveys had found, most of them small, dim, and lurking, at distances so great that even Hubble could only detect the bright fraction of them. 2 trillion galaxies, each containing anywhere from a few million to several trillion stars. If you summed the stellar populations across the entire observable volume, the total number of stars would be approximately 10 to the power of 24, 1 septillion. Written out in full, that number requires a 1 followed by 24 zeros. There are more stars in the observable universe than grains of sand on every beach, in every desert, covering every ocean floor across the entire surface of the Earth. The comparison is not approximate. It has been calculated. The number of grains of sand on Earth is estimated at roughly 10 to the 19th power. Stars in the observable universe outnumber them by a factor of roughly 1,000,000,000. Every one of those stars is a nuclear furnace. Every one of them has spent millions or billions of years fusing hydrogen into heavier elements, manufacturing the raw materials of planets and potentially life. Every one of them occupies a specific position in the cosmic web in a filament near a node along a wall or in the sparse outskirts approaching a void. And every one of them is so remote, so embedded in distances that make the Milky Way invisible that it will never be visited. never be named by a human being, never be anything more than a statistical entry in an astronomical census. The James Webb Space Telescope, launched on Christmas Day 2021 and placed at the second Lagrange point 1 million miles from Earth, has begun pushing the observational frontier toward the very edge of the observable sphere. Its instruments, optimized for infrared wavelengths that can penetrate dust clouds and detect the redshifted light of the earliest galaxies, have already rewritten our understanding of the universe's first billion years. In January 2026, astronomers confirmed the discovery of a galaxy designated JADESGSZ140, verified as the most distant galaxy ever spectroscopically confirmed. Its light reveals the universe as it appeared just 280 million years after the Big Bang, a mere 2% of the universe's current age. The galaxy is currently located approximately 33.8 billion light-years from Earth, a figure that reflects the expansion of space since the light was emitted. It is brighter, more massive, and more chemically enriched than any theoretical model had predicted for a galaxy forming so early in cosmic history. 280 million years after the Big Bang, the universe was barely an infant. The first stars had only recently ignited. The cosmic web was just beginning to assemble its first tendrils, and already a galaxy containing hundreds of millions of stars and detectable quantities of elements heavier than hydrogen and helium was shining in what would become our corner of the cosmos 13.5 billion years later. The James Webb Space Telescope has not merely pushed back the observational frontier, it has revealed that the early universe was assembling complex structures with a speed and efficiency that challenges the models we built to explain it. Roughly 100 times more luminous early galaxies have been detected than standard cosmological models anticipated. Galaxy formation in the infant universe was far more vigorous and far more mysterious than anyone expected. The question the telescope is forcing theorists to confront is not a minor calibration issue. It suggests that either our models of how matter clumps and collapses in the early universe are missing something significant, or the initial conditions after inflation were more favorable for rapid structure formation than our current measurements of the cosmic microwave background imply. Either answer requires new physics, or a significant revision of existing physics. The frontier of human knowledge is moving, and James Webb is the instrument pushing it. But the James Webb Space Telescope, for all its extraordinary reach, cannot see past a certain boundary. No telescope built from ordinary matter and operating on electromagnetic radiation ever will. That boundary is the cosmic microwave background. The cosmic microwave background radiation is the oldest light in the universe, the first electromagnetic signal ever to travel freely through space. Before it was emitted, the universe was an opaque fog. In the first 38,000,000 years after the Big Bang, the cosmos was so hot and so dense that photons could not travel more than microscopic distances without colliding with free electrons and being scattered in a new direction. The universe was in effect a plasma so thick with charged particles that light was trapped, unable to propagate, unable to carry information from one place to another. Then 38,000,000 years after the Big Bang, something changed. The universe had been cooling as it expanded. When the temperature dropped to roughly 3000 degrees Kelvin, hot by everyday standards but cool enough by the standards of the early cosmos, electrons began combining with protons to form the first stable hydrogen atoms. This process, called recombination, removed the free electrons that had been scattering photons. The fog cleared. Light was suddenly free to travel. And it has been traveling ever since. That primordial light, released 38,000,000 years after the Big Bang, streaming through space for 13.8 billion years, now arrives at Earth from every direction simultaneously. The expansion of the universe has stretched its wavelengths from the visible into the microwave portion of the electromagnetic spectrum, cooling it from its original 3000 degrees to approximately 2.725 degrees above. Absolute zero. It is extraordinarily uniform. In every direction astronomers look, the temperature is the same to within a few hundred thousandths of a degree. The sky, viewed in microwave wavelengths, is an almost perfect sphere of ancient light at almost perfectly uniform temperature. Almost, not quite. The Planck satellite, the most precise instrument ever built to measure the cosmic microwave background, mapped those tiny temperature variations across the entire sky with extraordinary resolution. Warmer spots corresponding to regions that were slightly denser, 3,800,000 years after the Big Bang. Cooler spots corresponding to slightly less dense regions, fluctuations of 1 part in 1,000,000, imprinted across the entire celestial sphere, the fossil record of the quantum fluctuations from inflation preserved in ancient light readable across 13.8 billion years of cosmic history. Every galaxy, every cluster, every filament of the cosmic web, every structure we have described in this entire journey traces its ancestry to those faint temperature ripples in the cosmic microwave background. The seeds of the Milky Way of Andromeda, of the Virgo cluster of Laniakea, all of them are visible in embryonic form in the pattern of the oldest light in the universe. The cosmic microwave background also sets an absolute limit on electromagnetic observation. Before recombination, no light traveled freely. There are no photons carrying information about the first 3,800,000 years of cosmic history. That period is permanently hidden behind the wall of ancient radiation. No optical telescope, no radio telescope, no X-ray observatory, no gamma-ray detector will ever see through it. The first 3,800,000 years of the universe are observationally inaccessible to any instrument that detects electromagnetic radiation. Other windows may eventually exist. Gravitational waves' ripples in spacetime itself decouple from matter in the first fraction of a second after the Big Bang, far earlier than photons. A primordial gravitational wave background, if detected, would carry information from epochs no photon has ever seen. Experiments including LIGO, Virgo, and the future space-based LISA observatory are working toward the sensitivity required to detect such signals. The detection would be one of the most significant scientific achievements in human history, a direct observation of the universe's first moments. But for now, the cosmic microwave background is the last war, the furthest we can see, the oldest portrait we possess of a universe barely emerged from its birth. Beyond the observable universe, beyond the 46.5 billion light-year horizon, in every direction lies more universe. How much more is a question that current physics can constrain but cannot definitively answer. The most rigorous approach uses measurements of the large-scale geometry of space. If the universe is positively curved like the surface of an enormous four-dimensional sphere, then the angles of very large triangles drawn in space would sum to slightly more than 180 degrees. If negatively curved, slightly less. If perfectly flat, exactly 180. The Planck satellite's measurements of the cosmic microwave background constrain the curvature of space to be flat, within a measurement precision of roughly 0.4%. This flatness implies that the universe is either infinite or so vastly larger than the observable portion that its curvature is too gentle for any instrument we could build to detect. Statistical analyses based on Planck data suggest that the total universe is at minimum 250 times larger in radius than the observable volume, corresponding to a minimum total diameter of roughly 23 trillion light-years. If that conservative lower bound is correct, the observable universe we can see occupies less than 1 part in 15 million of the total cosmic volume. For every galaxy, we can observe at least 15 million more exist beyond our horizon. And that is the most conservative possible estimate. If the universe is truly flat, if the curvature is exactly zero rather than merely close to it, then the universe is infinite. Not very large, not almost infinite. Infinite, an unbounded expanse of space, extending without limit in every direction, containing an infinite number of galaxies, an infinite number of stars, an infinite number of planets. The implications of a genuinely infinite universe are not merely large, they are philosophically destabilizing in a way that nothing else in science quite matches. In an infinite universe, with uniform physical laws in a cosmos, where the same constants of nature and the same equations of physics apply everywhere. Every configuration of matter that is physically possible must occur somewhere. Not probably, not approximately, certainly, an infinite number of times. If you could travel far enough farther than any observation could ever confirm, into regions of space so remote that no signal from there will ever reach us, you would find regions where the arrangement of matter mirrors our own solar system exactly. Regions where a planet identical to Earth orbits a star identical to the Sunday. Regions where a person who is in every measurable physical sense identical to you is reading words identical to these. In an infinite universe, nothing is unique. This is not a metaphysical speculation. It is the straightforward mathematical consequence of infinity applied to a finite set of possible physical configurations. The number of ways matter can be arranged within a given volume of space is enormous, but finite, bounded by quantum mechanics and thermodynamics. If space is infinite, every possible arrangement must repeat an infinite number of times. Whether this is true depends on whether the universe is actually infinite or merely very large. We cannot know. The physics of cosmic inflation, the mechanism that likely produced the observable universe we inhabit, naturally generates regions of space far larger than what we can see, but whether those regions extend without bound or eventually reach an edge depends on details of inflation's dynamics that current measurements cannot resolve. We live, in other words, at the edge of the knowable. The observable universe is defined not by the limits of our technology, but by the limits imposed by the laws of physics, the finite speed of light operating in an expanding cosmos. Build a better telescope, and you can see farther into the past, deeper into the history of the observable volume. But you cannot see beyond the horizon. You cannot receive a signal from a region of space that is receding faster than light. You cannot communicate with, observe, or be influenced by anything outside the causal boundary that surrounds every observer in this universe. And that boundary is shrinking. In 1998, two independent teams studying distant type, Ia supernovae Brian Schmidt and Adam Rees, leading one group, Saul Perlmutter, leading the other, discovered something that overturned the prevailing expectation of cosmology. The expansion of the universe is not slowing down, it is speeding up. Distant supernovae appear dimmer than expected, farther away than they should have been if gravity were decelerating the expansion. Something was pushing space apart with increasing vigor, overcoming the gravitational attraction of all the matter in the universe and accelerating the cosmic expansion. That something was labeled dark energy, a name chosen to signal how little we understand it. Dark energy constitutes approximately 68% of the total energy content of the universe. Dark matter makes up about 27%. Ordinary matter, the atoms and molecules that build stars, planets, oceans, and people, accounts for roughly 5% of the total. The universe is overwhelmingly composed of substances whose fundamental nature remains entirely unknown. The matter you are made of, the matter that has been the subject of every physics experiment ever conducted, every chemistry equation ever written, every biological process ever studied, that matter is a 5% minority in a cosmos dominated by things that have never been directly detected and are not understood. Dark energy's accelerating expansion has a consequence that accumulates quietly across cosmic time until it becomes devastating. Galaxies beyond a certain distance are currently receding from us faster than the speed of light. Not because they are moving through space faster than light, nothing does that as Einstein's special relativity forbids it, but because the space between us and them is expanding faster than light can cross it. Light emitted by those galaxies today will never reach us. They are beyond our cosmic event horizon. We cannot observe them, signal them, or interact with them in any way. They are, for all practical and physical purposes, gone. And the number of galaxies beyond that horizon grows with every moment that passes. In approximately 100 billion years, roughly 7 times the current age of the universe, if dark energy continues behaving as current measurements indicate, every galaxy beyond the local group will have receded beyond the cosmic event horizon. The Virgo cluster, which currently pulls us gravitationally even as it recedes, will have passed beyond the point where any signal from it could ever reach us. The Coma cluster, the Perseus cluster, the Shapley supercluster, all of them will be gone. The Laniakea Supercluster will have dissolved its constituent galaxies, scattered beyond the observable horizon by the relentless expansion. What will remain visible from the Milky Way, or rather, from the merged Milky galaxy that will have formed by then, will be only the immediate gravitational family, the local group. A few dozen galaxies in a sphere, perhaps 10 million light-years across, surrounded by an expanding emptiness that stretches dark and silent to infinity in every direction. A civilization arising in that epoch would look out into the sky and see a single large galaxy, their home surrounded by perhaps a dozen satellite galaxies and a scattering of dwarf companions. No clusters, no filaments, no evidence of the cosmic web, no cosmic microwave background detectable by any conceivable instrument. Its wavelengths stretched by trillions of years of expansion to lengths so extreme that detecting them would require an antenna larger than the observable universe of that era. The evidence for the Big Bang, for the existence of other galaxies, for the cosmic web, for the entire story we have been telling, would be irretrievably gone. Those future astronomers, no matter how brilliant, would have no observational basis for concluding that the universe extended beyond their local island of light. They would have no way to know that 2 trillion galaxies once existed within their observational horizon. They would have no way to discover cosmic expansion, because there would be nothing left nearby to measure it against. The universe would appear to all instruments they could build to be a single large galaxy embedded in an infinite static void. They would be completely wrong about the nature of their universe, and they would have no way to know it. We are the fortunate ones. We exist in a brief window in cosmic history, a window that will not last long on any scale that deserves to be called astronomical when the evidence is still visible. The cosmic microwave background still glows faintly across the entire sky, detectable by instruments cold enough and sensitive enough to measure it. Distant galaxies still emit photons that arrive at our detectors after journeys of billions of years, carrying information about the large-scale structure of the cosmos. The cosmic web is still imprinted in the statistical distribution of galaxy positions across surveys covering billions of light-years. The expansion of the universe is still measurable, still mapped, still being refined with instruments like Euclid and the dark energy spectroscopic instrument. We can still piece together the story. This window will not remain open. The universe is slowly, systematically, irreversibly erasing the evidence of its own history, pulling the witnesses beyond the horizon one galaxy at a time, replacing a cosmos rich with observable structure with a darkness that deepens with every billion years that passes. We happen to arrive during the era when the story was still readable. That is not nothing. That is in fact everything. 1658. Claude responded, "Now stand back. Now stand back." Not metaphorically. Imagine it physically. Imagine stepping away from everything we have described. The galaxies, the filaments, the voids, the ancient light, the accelerating expansion, and finding a vantage point from which the entire journey is visible simultaneously. Not sequentially the way we have traveled it, one scale dissolving into the next. All of it at once. Every distance we have crossed, every structure we have named, every number we have sat with, arranged in a single frame. What you would see is not what you expect. You would not see a collection of large things. You would see a set of nested containers, each one swallowing the previous so completely that the previous becomes undetectable. Not smaller, not reduced, gone. Erased by the mathematics of scale in a way that has no analogue in ordinary human experience and cannot be conveyed by any metaphor that does not eventually break down. But let us try anyway. If you represented the entire observable universe as a sphere the size of the Earth, a globe 8,000 miles across placed in front of you, the Laniakea Supercluster would be the size of a city, roughly 70 kilometers in diameter, a city embedded inside a planet. Detectable, but already small, the Virgo cluster would shrink to a few kilometers across a neighborhood within that city. The local group would compress to just over a kilometer, a few city blocks. The Milky Way, this galaxy of 400 billion stars and 1.5 trillion solar masses, a structure so vast that light needs 1,000,000 years to cross its luminous disk would be the length of a swimming pool. A swimming pool inside a few city blocks, inside a neighborhood, inside a city, inside a planet. And the solar system, the entire solar system from the sun to the outer edge of the Oort cloud, encompassing every planet, every moon, every comet, every object humanity has ever physically visited or touched, every machine we have ever launched. Into space, every signal we have ever sent would be smaller than a single bacterium. A bacterium inside a swimming pool, inside a neighborhood, inside a city, inside a planet. That is the compression, that is the actual ratio of scales between the cosmos we inhabit and the human world we navigate. And the compression is not approximate, it is not a rough illustration, it is what the numbers produce when you divide them carefully and honestly. The solar system is to the observable universe as a bacterium is to the Earth, not similar to that ratio to within the precision of the measurements involved. Now hold that image and ask yourself what it means. The natural response, the response that almost every person has when confronted with these numbers for the first time, is a specific flavor of despair, a sense of futility, a feeling that the scale of the universe is a statement about human insignificance, that we are so small, so brief, so peripheral, that our existence is cosmically irrelevant, that the universe has demonstrated through the sheer magnitude of its indifference that nothing we do or feel or think or build matters in any final accounting. This response is understandable. It is also, when examined carefully, a non sequitur. Significance is not a function of physical size. It never has been. A virus measuring 100 nanometers across can redirect the trajectory of an entire civilization. A mutation in a single gene can alter the course of evolution across millions of generations. A thought, a specific arrangement of electrochemical signals occupying a volume of roughly 1.4 liters of neural tissue can produce an equation that changes everything humanity will ever build. The relationship between physical dimension and importance is not the linear one our intuition suggests. The universe does not award consequence based on volume. What the scale of the cosmos actually reveals when you examine it without flinching is something far more interesting than human insignificance. It reveals the mechanism by which you came to exist. The universe is 13.8 billion years old and 93 billion light years across, not despite the fact that you exist, but in some deep sense because of it. Not in the sense of design that is a different conversation and not the one we are having here. In the sense of necessity, the physical processes required to produce a rocky planet orbiting a stable star covered in liquid water, rich in the heavy elements needed for complex chemistry, located in a galaxy old enough that multiple generations of stars have already lived and died, and seeded the interstellar medium with those heavy elements. Those processes require billions of years and billions of light years of space in which to operate. Stars need time to form, burn, and die. They need to scatter their products into the interstellar medium. New generations of stars need to form from that enriched material form rocky planets. Give those planets time to cool for oceans to stabilize, for chemistry to begin exploring the space of molecular complexity, for biology to emerge and evolve not once, not quickly, but across billions of years. Patient, incremental, extinction-punctuated development. The universe needed to be old enough for all of that to happen. And a universe 13.8 billion years old, expanding at the rate ours expands, is necessarily as large as the one we find ourselves in. The vastness is not incidental, it is the cost of the ticket. Consider the atoms in your body, not metaphorically, literally physically consider them. Your body contains approximately 7 times 10 to the 27th power atoms, 7 followed by 27 zeros. Most of them are hydrogen, the simplest element produced in the first 3 minutes after the Big Bang, when the universe was hot enough for nuclear fusion to begin and cool enough for protons and neutrons to assemble into light nuclei. The hydrogen in your body is as old as the universe itself. It has existed since a time when no stars, no galaxies, no planets, no chemistry of any complexity existed anywhere. It has spent most of its existence drifting through molecular clouds, cycling through stars, being ejected into the interstellar medium, being swept up by gravity into new structures for 13.8 billion years. The heavier atoms, the carbon, the oxygen, the nitrogen, the phosphorus, the sulfur, were not produced in the Big Bang. The Big Bang did not generate the elements needed for complex chemistry. Those elements were manufactured inside stars. Nuclear fusion in stellar cores fused hydrogen into helium, helium into carbon and oxygen into heavier elements in a sequence that required temperatures of hundreds of millions to billions of degrees and pressures found only in the interiors of massive stars. When those stars died, when they exhausted their nuclear fuel and exploded, they scattered those manufactured elements into the interstellar medium, where they drifted for millions of years before being gathered by gravity into the molecular clouds that gave birth to new stars, and around some of those stars, rocky planets, the iron in your blood, every iron atom in every hemoglobin molecule in every red blood cell in your body was forged in the core of a star that no longer exists. It was produced in the final stages of nuclear burning in a massive star that exhausted its fuel, collapsed, and exploded in a supernova that briefly outshone an entire galaxy. That iron was then scattered into the interstellar medium, where it drifted for perhaps hundreds of millions of years before being incorporated into the molecular cloud that collapsed to form the solar system 4.6 billion years ago. It settled into the protoplanetary disk, accreted into the early Earth, cycled through geological processes across billions of years, was incorporated into the ocean, was taken up by early biochemistry, and eventually found its way into the hemoglobin in your blood, where it binds oxygen atoms themselves, forged in different stars, and carries them through your circulatory system to sustain the neural processes that are right now processing these words. This is not poetry, it is chemistry, it is nuclear physics, it is the actual biography of the atoms in your body, reconstructible from isotopic signatures and stellar evolution models and geological records. You did not come from Earth. You came from the galaxy. Your body is the galaxy's autobiography, written in biological form, a temporary arrangement of atoms that have spent billions of years being processed through cosmic structures before arriving at this improbable configuration that happens to be capable of understanding the journey. Now consider the other end of the scale, not the atoms in your body, but the processes of your mind. The human brain contains approximately 86 billion neurons. Each neuron forms on average 7,000 synaptic connections, with other neurons producing a network of roughly 100 trillion connections, 10 to the 14th power, individual synaptic junctions through which electrochemical signals propagate at speeds of up to 120 meters per second. The number of possible states of the human connectome, the number of distinct patterns of activation that the neural network of a single human brain can theoretically occupy, is a number so large it exceeds the number of atoms in observable universe by factors that make the word large meaningless. Inside your skull sits a structure more informationally complex than the observable cosmos, not physically larger, informationally richer. The universe contains more matter. The brain contains more distinguishable states. And this brain, this 1.4-liter electrochemical network, assembled from atoms forged in dead stars, has done something that nothing else in the observable universe, across 13.8 billion years of cosmic history and 93 billion light-years of space, has demonstrated any capacity on to do. It has looked at the universe and understood it, not completely, not finally, but genuinely verifiably with increasing precision and depth. It has developed mathematics that describes the curvature of space-time. It has built instruments that detect gravitational waves from neutron star mergers a billion light-years away. It has decoded the nuclear processes in stellar interiors from the spectrum of light reaching our atmosphere. It has photographed the shadow of a black hole in a galaxy 54 million light-years distant. It has traced the large-scale structure of the cosmic web from the statistical distribution of galaxy positions across billions of light-years. It has measured the temperature of the oldest light in the universe to a precision of 1 part in a million. a species that evolved 3,000,000 years ago on a small planet orbiting an ordinary star in the outer suburbs of one galaxy among 2 trillion, has reconstructed the history of the universe from its first fraction of a second to its far future using instruments built from refined metal, glass and silicon, powered by chemical reactions, guided by mathematical abstractions that exist only as patterns in the electrochemical activity of biological neural networks. The universe has been doing things for 13.8 billion years. It has formed stars and destroyed them. It has assembled galaxies and torn them apart. It has grown the cosmic web from quantum seeds and expanded it across billions of light years. It has done all of this blindly, mechanically following the equations of physics, without awareness of any kind. And then, in the last instant of cosmic time, in a period so brief it does not register on any scale we have used in this journey, matter on one small planet arranged itself into a configuration that became aware of all of it. That is not a small thing. That is perhaps the largest thing. The solar system is a bacterium inside the observable universe. But the observable universe has never, in any of its 2 trillion galaxies across 13.8 billion years of history, produced any evidence of something that can sit and contemplate the solar system's smallness and feel the weight of what that means. We have found it in exactly one location, on one planet, in one species, possibly in many individuals within that species, though the depth of the contemplation varies. 1. Possibly. The cosmic web stretches across 93 billion light-years. It contains structures so large that single filaments span hundreds of millions of light-years. It has been building for nearly 14 billion years. And in all of that immensity, in all that space, in all that time, across all those stars and all those planets and all those molecular clouds and all those supernova remnants and all those colliding galaxies, the only place we have confirmed the existence of something capable of knowing the universe exists is here. This small planet, this thin coat of paint on a billiard ball, this grain of sand orbiting a grapefruit inside a swimming pool, inside a neighborhood, inside a city, inside the Earth, we used as a scale model for the observable universe. That fact can be read 2 ways. The first reading is the one despair produces: we are alone, isolated, cosmically irrelevant, a fluke in a universe that does not notice us and will not mourn us when we are gone. This reading is not wrong about the physics. The universe does not notice us. It does not have the capacity to notice anything. It is not structured for noticing. That much is true. The second reading is the one that emerges when you sit with the first reading long enough, when you push through the initial vertigo and come out the other side. If the universe does not notice us, then the only noticing that happens here. The only comprehension of the cosmic web that exists in the observable universe. The only awareness of what dark matter is, of how stars die, of what a light year means, of how old the cosmos is, of how large and how empty and how structured and how strange occurs in biological neural networks on the surface of this planet. We are not witnesses to the universe. We are the universe's only known means of witnessing itself. The cosmic web has existed for billions of years without being perceived. The ancient light of the cosmic microwave background has been crossing space for 13.8 billion years without being measured. The black holes at galactic centers have been consuming matter and sculpting the gas of their host galaxies without being photographed. All of it has been occurring mechanically and magnificently in the absence of any observer capable of knowing it was occurring. And then a species developed on a small planet and began tentatively to look, first at the sky, with naked eyes noticing patterns and regularities, and building the first primitive models of celestial motion. Then with lenses and mirrors that extended the reach of biological vision into wavelengths beyond what evolution had provided. Then with mathematics that could describe the behavior of objects no instrument had yet detected and predict the existence of phenomena no one had yet observed. Then with radio telescopes, X-ray observatories, gravitational wave detectors, space-based infrared observatories, placed at the gravitational balance points of the Earth-Sun system, to peer at the universe in wavelengths the atmosphere absorbs. Each new instrument revealed a new layer. Each new wavelength opened a new window. Each new window showed structure that had been there all along, unseen, unwitnessed, occurring without acknowledgement in the vast indifferent machinery of space-time. We have been here for 3,000,000 years. The universe has been here for 13.8 billion. We arrived if the universe's history were compressed into a single calendar year at approximately 1159 and 56 seconds on December 31st. We have been observing for less than a second of cosmic time, and in that second we have reconstructed most of the story, not all of it. The nature of dark energy remains unknown. The mechanism of inflation remains unconfirmed. The question of whether the universe is infinite remains unanswerable with current tools. The origin of the matter-antimatter asymmetry that allowed matter to exist at all rather than having every particle annihilate its antiparticle in the first second after the Big Bang, leaving a universe of pure radiation, remains one of the deepest unsolved problems in physics. The question of whether the awareness that is currently processing these words is unique in the observable universe, or whether it has arisen independently on other worlds, around other stars, remains open. These are not small gaps in our knowledge. They are fundamental questions about the nature of everything, but we are asking them. That is the thing that deserves to be noticed when you have followed the scale of the universe, all the way from a 6-foot figure on a small planet to the edge of the observable cosmos, and looked back. Not the emptiness, not the distance, not the indifference, the asking. A universe 13.8 billion years old, 93 billion light-years across, containing 2 trillion galaxies and 1 septillion stars, and an incalculable number of planets, has produced in at least one location, and possibly only one, something that asks questions about it, something that is not content merely to exist inside the universe, but insists on understanding it, something that finds the distances disturbing not because they are threatening but because they are interesting, something that builds instruments and writes equations and stays up late, looking at ancient light, and feels when the numbers finally sink in, not futile, but astonished. You are that something, not as a species, as an individual. The astonishment you feel right now, if you feel it, and if you have followed this journey carefully, you should, is the universe's astonishment at itself, experienced through the specific configuration of matter that is you. The curiosity driving you through this story is the same force that built the telescopes and launched the satellites and processed the data and wrote the equations that made the story possible to tell. The universe has no awareness of its own scale. You do. And that awareness, however brief, however fragile, however local, is the most extraordinary fact contained within the 9.3 billion light-year sphere of everything we can observe. Everything else is just distance. There is a photon traveling towards you right now. It left a star you will never see in a galaxy that has no name in any human language at a distance, so remote that the civilization capable of naming it does not yet exist and may never exist. It has been traveling for billions of years through the intergalactic void, through the perfect emptiness between filaments of the cosmic web, through regions so cold and so empty that a single cubic meter of space contains fewer atoms than you can count on one hand. It crossed the boundary of the local group. It threaded through the sparse intergalactic medium between galaxy clusters. It entered the Milky Way, passed between stars, separated by light years of vacuum, navigated the thin disk of our galaxy without striking anything, and descended through the atmosphere of this small planet. In a moment that cannot be precisely predicted, it will reach your eye. It will interact with a photoreceptor cell in your retina. It will trigger an electrochemical cascade that propagates through your optic nerve into the visual cortex of your brain. And in that instant, in that exchange between an ancient particle of light and a temporary arrangement of biological matter, the universe will have completed a transaction that took billions of years to arrange. You will see a star. You will not know where it came from. You will not know how far it traveled. You will not know that the star that produced it may already be dead, that the nuclear fire that launched that photon may have exhausted itself millions of years ago, collapsing into a white dwarf or a neutron star or a black hole, leaving behind a cold remnant in a galaxy no telescope has yet examined. The star's death will be information still in transit carried by later photons that have not yet arrived, that may not arrive for millions of years more. You will simply see a point of light in a dark sky, and if you have made this journey with us tonight, that point of light will never look the same again. This is where we began, in a sense, not with a number or a distance or a scale, with a question so large it could not be asked directly, only approached slowly through layers of accumulating context. How big is the universe? Not in the sense of what number to write down, in the sense of what it means to exist inside something that large, what it does to the way you understand your own life, your own planet, your own moment in cosmic time. The answer is not a number. The answer is a feeling that the numbers, when they finally sink in, produce. A feeling that is not quite despair, and not quite comfort, and not quite awe, though it contains elements of all three. A feeling of being simultaneously the smallest thing imaginable, and somehow the most significant. Not because the universe has made any declaration about human importance, but because the universe has made no declarations at all, and we are the only thing we know of that has noticed the silence and decided to fill it with understanding. Here is the chain of containment, stated one final time, stripped to its essentials. You are on a planet 8,000,000 miles across. That planet orbits a star 93 million miles away. That star is one of 400 billion in a galaxy, 10,000,000 light years across. That galaxy is one of more than 80 inches, a local group, 10 million light years in diameter. That group is falling toward a cluster of over 1300 galaxies, 54 million light years away. That cluster is one node among many in a supercluster, 500 million light years in extent. That supercluster is threaded into a cosmic web of filaments and voids spanning billions of light years. And all of it, every filament, every void, every galaxy, every cluster, every supercluster, every thread of the web exists within an observable sphere, 93 billion light years across, that may represent less than 1/15 millionth of what actually exists. Each structure in that chain contains the previous one, the way an ocean contains a single molecule of water. Each transition from one scale to the next rendered the previous scale invisible, not smaller, not reduced, invisible, gone, below the resolution of any map, beneath the threshold of any measurement, rounded to zero by the arithmetic of cosmic proportion. And at the beginning of that chain, at the smallest end, at the level where the numbers become too tiny to register on any cosmic instrument, sits something that traced the entire chain from bottom to top and understood what it found. That is you. That is this. That is the thing that is happening right now, in the 1.4 liters of electrochemical activity behind your eyes, as these words complete their transit from the page into comprehension. The universe has been running for 13.8 billion years. For most of that time, for the first several billion years, while stars were forming and dying and scattering heavy elements, and new stars were forming from the enriched debris, there was nothing in the observable cosmos capable of knowing any of it was happening. The cosmic web was assembling in the dark, unobserved. The cosmic microwave background was crossing space in every direction, carrying the imprint of the universe's first moments, with no instrument to receive it. Black holes were consuming matter and growing in the centers of galaxies with no one to photograph their shadows. Supernovae were briefly outshining their host galaxies and seeding the interstellar medium with iron and oxygen and calcium, with no one to measure the yield. All of it occurred in the absence of any witness. And then in the last eye blink of cosmic time, matter on one small planet became aware, not fully, not permanently, not certainly for much longer given the various ways that consciousness can be extinguished, but genuinely, undeniably, with a depth of comprehension that has been growing for tens of thousands of years and shows so far no sign of reaching its natural limit. We do not know if this has happened anywhere else. The search continues with radio telescopes scanning for artificial signals with the James Webb Space Telescope, examining exoplanet atmospheres for chemical signatures of biology, with mathematical models attempting to estimate the probability of complex life arising given what we know about planetary formation and biochemistry. The answer has not been found. The silence of the cosmos on the question of whether other minds exist within it remains total and unbroken. That silence is not proof of uniqueness. The distances are too large, the timescales too vast, the methods of communication too constrained by the speed of light for absence of evidence to constitute evidence of absence. A civilization in the Andromeda galaxy, signaling in our direction with the most powerful transmitter imaginable, would have sent that signal 2.5 million years before we had any instrument capable of receiving it. The universe is too large and too old for the silence to mean what it would mean on a human scale. But the silence is real, and in the absence of any confirmed signal, any confirmed detection, any confirmed biosignature from another world, we sit with the following possibility that in a sphere 93 billion light-years across, containing 2 trillion galaxies and 1 septillion stars, the only confirmed instance of matter that has become aware of the universe is here, on this planet. In this thin biological layer on the surface of a small rock, orbiting an ordinary star in the outer suburbs of 1 galaxy among 2 trillion. If that is true, then the most extraordinary thing in the observable universe is not a quasar outshining its entire host galaxy. It is not a neutron star spinning 700 times per second with a magnetic field 1 trillion times stronger than Earth's. It is not a filament of the cosmic web stretching 500 million light-years through the intergalactic medium. It is not even the cosmic microwave background, that ancient wall of light carrying the imprint of the universe's first moments across 13.8 billion years of expansion. It is this. Whatever is happening inside you, as you sit with these numbers and feel their weight, the specific sensation of comprehension mixed with vertigo, mixed with something that does not have a clean name, that response to encountering the scale of things, that involuntary recalibration of every assumption your nervous system has ever made about the size and significance of the world. That is the most extraordinary thing we have found in the observable universe, because it is the only thing in the observable universe that we know finds anything extraordinary. The universe does not experience wonder. You do. The universe does not measure distances. You do. The universe does not feel the weight of 93 billion light-years pressing against the walls of a 1.4-liter brain and find that weight astonishing. You do. And all of it, the measuring, the feeling, the astonishment, is temporary. That is the other truth that sits alongside the wonder, and it would be dishonest to omit it. The atoms in your body will not remain in this configuration for long on any scale that deserves to be called cosmic. The electrochemical processes that produce your awareness will cease. The specific arrangement of matter, that is you, will dissolve back into the world, and the atoms will begin their next journey into soil, into water, into the food chains of whatever organisms inhabit this planet in the centuries. After you are gone, eventually into the atmosphere, eventually perhaps into space, eventually back into the interstellar medium when the sun exhausts its fuel and the solar system disperses. Your atoms will continue. You will not. The universe will continue long after every trace of human civilization has been erased, long after the sun has swelled into a red giant and consumed the inner planets, long after the Milky Way and Andromeda have merged into Milkomeda, long after the last stars have exhausted their fuel and cooled to black dwarfs drifting through an expanding darkness, long after the last black holes have evaporated through Hawking radiation into a final thin dispersal of photons, long after the observable universe has stretched so thin that its average energy density approaches absolute zero and the last coherent structures dissolve into thermal equilibrium. All of that will happen. The timescales are almost incomprehensible. 10 to the 100th power years for the last black holes to evaporate, durations that make the current age of the universe look like the first Planck time after the Big Bang. But it will happen. The universe is not a permanent structure. It is a process. A long, slow, extraordinarily complex process that began in a state of almost perfect uniformity and is moving through the patient arithmetic of thermodynamics toward a state of perfect uniformity again. We are in the middle of that process. In the brief, improbable, thermodynamically unlikely middle, where complexity has been able to arise and persist, where stars have been burning and planets have been cooling and oceans have been churning and chemistry has been exploring and biology has been evolving and minds have been developing, before the long, slow, inevitable return to equilibrium reclaims everything that was temporarily borrowed from the gradient. This moment, this specific configuration of matter and energy and awareness, this will not recur, not in any meaningful sense, not with any continuity of identity or memory or experience. The atoms will scatter. The information encoded in your neural architecture will dissipate. The specific pattern of electrochemical activation that constitutes your experience of reading these words will cease, and the universe will continue its long arc toward equilibrium without any record of the fact that it occurred. And yet it is occurring, right now, undeniably, with a richness and a depth and a precision that the universe spent 13.8 billion years creating the conditions to make possible. That is not nothing. That is, by any honest accounting, the most improbable and the most remarkable thing we have found in the 93 billion light-years we can see. So look up tonight if the sky is clear where you are. Go outside and find a dark place away from the lights of the city and lie on your back and look at what is there. The stars you can see with naked eyes are all within a few thousand light-years of Earth. A tiny, tiny neighborhood within the Milky Way itself. A tiny neighborhood within the local group itself, invisible on the scale of Laniakea itself, invisible on the scale of the cosmic web, itself invisible on the scale of the observable universe. What you will see represents an almost unmeasurably small fraction of what exists. And yet it will be enough. It will be more than enough. Because the light entering your eyes in that moment will have been traveling some of it for thousands of years to reach the precise arrangement of matter that you are in this precise moment of cosmic time on this precise small planet. And when it arrives, it will be received by the only thing we know of in the observable universe that looks at light from distant stars and feels something. The universe spent 13.8 billion years building the conditions for that moment. Do not waste it. The photons are already on their way. They have been traveling since before your species existed, crossing distances that collapse every scale of human experience into irrelevance, threading through the cosmic web and the intergalactic medium and the interstellar void, carrying light from fires that may no longer burn in galaxies that have no names. They are coming toward you at 670 million miles per hour. They will arrive tonight or tomorrow night, or on some clear night when you finally go outside and look up and let the sky be as large as it actually is. And in the moment they reach you, in the instant that ancient light completes its billion-year journey and lands on the retina of a temporary arrangement of stardust that somehow learned to wonder, the universe will have done the most extraordinary thing it has ever been observed to do. It will have seen itself. That light is real. That moment is coming. And when it arrives, remember what you now know about how far it traveled to find you. It crossed everything. It came all this way. For that,